So, welcome everyone to the lecture number 8 on statistical theory for deep learning. We are on our way to prove an approximation result for deep neural networks with ReLU activation function. And we started with the first result, which is not shown here on the slide, that we can approximate the univariate function x maps to x squared by a deep neural network. We use this to prove lemma 2.3, that sigma be the ReLU activation function, let a be greater or equal 1. Then for any r in n, there exists a network f mult hat, which has r hidden layers and at most 18 neurons in each layer, such that f mult of hat mult of xy minus the product of x and y in absolute value. The absolute value of the difference is bounded by 2 times a squared times 4 2 minus r. So altogether you have only the linear in r many neurons, but you can or weights, but you can neurons and weights, but you can approximate the product exponentially with an accuracy which goes exponentially r. And we need to extend this to products of more than 2 terms, and if I want to multiply d different variables, then the simple idea is just pairwise multiply them and apply pairwise this network from lemma 2, 3. This will give us lemma 2, 4. Sigma is again the ReLU activation function, a is greater or equal 1, and this time d, the number of parameters which it has, is natural number, or number of real values which you want to multiply as natural number. And then for any r in n, which satisfies the lower bound, r must be greater than the log with basis 4 of 2 times 4 to the power 2d times 8 to the power 2d. There exists a network f hat mult d, which has r times log t sealed to the next number, natural number, many hidden layers, and 18 times d many neurons per hidden layer, such that f hat mult d of the d-dimensional vector x minus its product of all its components, and the difference in absolute value is less than 4 to the power 4d plus 1 times a to the power 4d times d times 4 to the power minus r. And the constant in front to 4 to the power minus r is not important, but important is the 4 to the power minus r here again. For all x, where each of the d-dimensional components is in the interval minus a to a. And that's what I want to prove today. And then we can prove our main result with that. And the proof is simple, but a little bit technical. Proofs goes as follows. I start with the network f mult from lemma 2.3. And that's a network in space of all ReLU neural networks with r hidden layers and 18 neurons. And now the question is, what do we have to multiply? Well, not only just values from minus a to a, because each of the components is minus a to a, but then I make products and then multiply these products so that they get larger. So I have to choose this product larger. That should be the network of lemma 2.4, lemma 2.3. Well, we have an error bound. Y minus xy something, and it's the 2 times the a squared, and the question is what a is. X squared times 4 to minus r, that's what I have to choose for all xy. And now I have to use my new value of a, which I want to use, and use the interval from minus a to a. Now the question is, what is the right thing? Well, if you think about it, these products are up to, well, I will recursively define it. So if you consider the product of all of them, then it will be something like a to the power d, the other one. So I could try with a to the power d, but one point is that I will use successively f mult to multiply them, and then I make an error. So I don't get the product, I get the product plus some error, so the range gets a little bit larger. So I have to add something, and I don't try to optimize the constant here, I make it just such that the proof is a little bit easier. So I make it very large, I make it minus 4 to the power d times a. You will see in the proof why I use this number. So, and then I get here something like, of course, I have to replace 4 to the power d by a to the power d. And in fact, I think the proof also works with 2 to the power d, and I didn't try to optimize the constants, because this 4 to something doesn't matter. So that's the first thing, that's the basic thing which we'll use. Then I said well, I will successively group my x1 to xd into pairs of 2, and I will need something like q equal log 2d groups. And I make again the ceiling, make it larger. And then I define my input which I will use. That's my Z1. Q. And here I use all my x, coordinates of x. That's x1 to xd. And then 2 to the power log 2d, where you make a ceiling, it might not be d, it might be larger, so I extend just by once. Here I have 2 to the power q minus d times this once. And now in the first layer, I multiply Z1, Z2, Z3, Z4, Z5, Z6, and so on until Z2 with exponent q minus 1 to exponent q. In the first layer, of f mod d or u mod d, you compute, while I compute f mod, maybe I should make a hat here too, because we had this hat notation of Z1, Z2. Then I compute the next one. Z4 until the last one is mod q minus 1. This one. now how many neurons do I need for this? Well, I need as many neurons. Well, these are 2q . 2 is power q divided by 2 many times I apply a command. So I need 2 to the power q minus 1. And now as many neurons as I need in f mod, and these are 18. And now if you think about the definition of q, then q is the ceiling of log 2d, so q minus 1 is less equal than log 2d, so 2 with exponent q minus 1 is less than 2 with exponent log 2d, so it's less equal than 18d neurons. And next we make the same thing with this, we multiply this 2 with exponent q minus 1 yeah, and there's a mistake, yeah, it's not the first layer. What do you see? I can't do this in one layer yet, because my neural network needs, fmult needs R layers. So in the first R layers, now we do the same thing with the next R layers, but with 2q minus 1 outputs. So we repeat. It is for QQ minus 1 outputs. So I take the first output together with the second output, multiply it. Take the third output together with the fourth output, and multiply it, and so on. Again, I need, this time I need 2 times q minus 2 times 18, so this will be 9 times d, but it's less than 18 times d neurons and R layers. And then I apply this, how many more times? How many more times? Well, until the output is only 1, yeah? So if I apply it say again and again, until one output is left. Which we call, and that's our fmult. So now the question is, how many layers do we need? How many neurons do we need?
So every time we take R layers, we need 18 times D
change we need at most 18 times d neurons, yeah?
We need to chain q many of these layers together, so we need r times q many layers with 18 times d neurons.
So for this we need r times q, and that's exactly what is in this theorem, that's the r times log 2e. Knows d neurons. So we have our network. Now we have to show that the error bound is satisfied. And for this we will apply all the time the error bound for the F minus. Question?
We need 18 times d neurons.
18 times d neurons, thank you. I said it, but wrote it in the wrong way. Now the question is, what happens if we multiply all these things together? And what is the error? So I want to apply this inequality here, this error bound, but then I have to be sure that the outputs are in the right range. So we have to think about where are the outputs in. Okay, how did I write it here? Okay, I make something strange and then I will see why it's useful. For L in 1, 2. Or to D. Yeah. Make it 1 to D. And Z1, Z1. Z1, Z2 in minus 4L minus 1 times in this 4L, 4 is explored L minus 1 L. I want to give an upper bound on the absolute value of F mul Z1, Z2. Well, that's less than if I bound the product plus the difference between my estimate and the product. Now the product itself is less than the product of these guys here, and each time is bounded in absolute value by 4L minus 1, 4 with exponent L minus 1 times AL. So it's 4L, product is 4L minus 1 squared times A2L. And this F mult had this bound is satisfied. And Yeah, and we want to do it in that way. Okay, we use this bound. 2 times 4EAD squared times 4 minus R. That is inequality, which I can mark as star. And the star is here. And now you see why I needed my lower bound on R. My lower bound on R in my lemma ensures me, well, R is greater equal than log with basis 4 times 2 times 4 with exponent 2d times a with exponent 2d. So 4 with minus R is less equal than 1 divided by this. So that's less equal than lower bound on R than 1. Plus 1. And now I can add here an a with exponent 2l, because a is greater or equal than 1. Make an upper bound. Then you see what's basically happened, that you add 1 to this one, but if you multiply out with the binomial formula, you see the whole thing is less than equal to 4 to the power 2l times 8 to the power 2l. Or maybe 4 to the power 2l minus 1. 8 to the power 2l. Is this correct? Because we have here I have at least you have 4 to the power 2l here, yeah? You have a plus 1, but you have a plus 1 from this one, so plus 2, but you got a minus 2 times 4 to the power 2, 4 to the power l, and that's less than, or the thing is less than minus 1. And now you see why I didn't use a 2 to the power l, because I think this 2 to the power l will be a point for l equal 1, 1. Oh no, I think it's 2 to the power l doesn't. So what does this imply? This implies, well, observe that our input at the first level satisfies this with l equal to 1, this bound. So after the first level we have this bound with l equal to 2, and then we make this bound again. So we have it with l equal to 4, then we get it with l equal to 8, and so on. So after the else, or after 18, after r times l many layers, our output after r times l many layers, our output is the interval this interval minus 4 to the power 2l minus 1 times 8 to the power 2l and 4 to the power 2 minus 1. And so in particular, our outputs will all the time be, oh no, that's not true. Because each time this L is doubled, so it's 2 to the power L. And that means that all the time the thing which we plug into F mult, they will be in the interval, well, 4 to the power 2q minus 1 times 8 to the power 2. So, or they will be bounded in absolute value by 4 to the power 2q minus 1 and 8 to the power 2q minus 1. And that's basically bounded by 4 to the power d times 8 to the power d. So we are all the way with multiplying in the bound where we are in the multiples. Okay? Questions? You see, maybe it's trivial, but somehow ugly or technical. You just have to do it here. And now we can finish it. Finish it real quickly by saying I define a function f hat with index 2 to the power q, depending on variables z1 to z2 to the power q, which won't be the same as the one which I used already in the construction of the network. So these are now, and that's just the what? The product from half of them and the product of half of them is described by q minus 1 and the second half now I have to start with set q minus 1 plus 1 until q. And of course I have to say where do I start? I have to start with f2. That is just as z1, z2. And then you see what my network basically computes is this guy with the q equal to the log 2d ceiling of it. So we see what we have to show is one more definition. I define L is equal to the supremum over all Z1 with 2L interval minus AA of f hat 2 to the power L from Z1 to minus its product. And then you see that what I'm interested in is my error bound. That's d of x minus how much Well, the f hat mod d is basically the f hat 2 to the power q of z1 to z2q with these special values which I defined at the beginning of the proof of z1 to zq. The product of the d component of x is basically the product of the 2 to the power q many z1 to z2 to the power q. So you see that whole thing is less equal than delta q. So what I actually prove is the bound on delta q. And that's the remainder of the proof. Questions? So this basically describes what we do in each of these R layers which we put together from this part. So that's basically the output of our neural network, and then I consider the worst error which I can do with that. That's the key. And now I make a recursive bound on delta q. Well, if you think about delta 1, we have delta 1 is the supremum over z1 to z2 in A. That's for L equal 1, I need an f hat 2. The f hat 2 is just f mult. And minus the product of z1 and z2. But that was a property of our neural network of mult, which we have chosen at the very beginning. It's this bound. So that's less equal to a star 2 to the power 4 with exponent 2d times a with exponent 2d. Times 4 to the power minus r. And now I make a recursive bound. So I relate delta L to delta L minus 1, or I make it directly with delta Q. Or maybe make it with delta L, makes more sense. And for 2 to we have delta L. That's by definition supremum over Z1 to Z2 to power L. Minus A. Then we have an F mult of, well, we have this F hat 2L, but this F hat 2L is just the F mult, F hat mult, this F hat 2L minus 1. From Z1 to Z2 minus 1. And I've had 2L minus 1, the product of the second half of our terms. Z1 and 2L minus 1 plus 1 and 2L. This one, and I subtract the product of all of them. This guy. And now we make the triangle inequality. Instead of considering this difference, we first look at how far is this guy from the product of its arguments. Then how far is the product of these arguments from, well, the product of the first argument and the second part of this one, and then how is the product of the first argument and the second part from this one, from this guy. And I use the triangle inequality to fill it up in 3 times, and the supremum over a sum is less the sum of the supremum, so we get the supremum over is equal supremum over Z1 to Z2L. Okay, so we have this F mult. F hat minus 1, Z1 to Z2 minus 1, and and now I just subtract the product of its arguments. First term. Now I have to add this term again. And forget about this one because it's the same. So I have this guy. Minus 1. And then go to 2L minus 1 times minus 1 from Z 2L minus 1 plus 1 Z 2L. And I subtract. I want to come to this guy, but I first subtract, well, it doesn't matter how I start. Maybe I start with the real product. This guy and one more. Last one is coming here. Same supremum term here. Times head. Minus the product, which are really interesting. Now I claim you can easily bound each of the three terms which we have. And I think there's an error because I don't want to make this until. Do I want to make it until Q? Yeah, we want to make it until Q. It's correct, no, it's correct here. Q is to write up about. We should start with 2 and until Q. Okay, now we need 3 other ones. Any ideas? First supremum. Excuse me, the first supremum?
The first supremum is upper bounded by lemma 2.3.
It's bounded by lemma 2.3, so it's basically bounded by our star, yeah? Because that's just one of these guys. If you make sure that these guys, the arguments, are in this interval, but that was this argument, where did I, what? It was this argument here, yeah? So that if you, that after L times L many layers, our output is in this interval, so it's always in, for L less equal than Q, it's always in this interval, which we, or L is at most Q minus 1 here, because for these guys we have only L minus 1, so it's in the interval star. So we get by star, that's less equal star. We can bound this by 2 times 4 to the power d and 3d squared times 4 to the power minus 1. That was the first term. What about the second term? So the second term is this guy here. So you see what you can do. You can move this one in front, then you have this f hat minus the product. This f hat with index 2 to the power L minus 1 minus the product is less than?
Delta L minus 1.
We get something like delta L minus 1. So we basically need to worry about the range of this guy here. Yeah? But the range of this guy here is? Well, what did you do here? You did multiply, you group and multiply how often? You have an interval, you have an computed product of 2 to the power L minus 1 many elements, yeah? So if you have one element, or if you have 2 elements, as a 2 to the power 1, then you just have to regroup one times, yeah? So 1 or 2. If you have 4, you have with this 2 to the power 2, you have 2 times, yeah? So basically you're doing L minus 1 times. So you are in the case that you have here R times L minus 1 many layers, and then you are in this range with power L minus 1. So I can make it such that, and I make a gap here. At the moment you will see later why I make this gap. You have 4 to the power 2L minus 1. So I make an upper bound, I forget about the minus 1, and A to the power 2 L minus 1. And then we have a delta L minus 1. And now I make the same thing for the third guy. What about the third guy? How do we derive an upper bound for the third term? What?
So we can factor out again the first, but then we factor the product of the zi.
You
First
do
to the power
factorize the product of the first 2 to the power L minus 1 many zi's. Yeah.
Then we again have left the f hat 2 to the power of L minus 1 minus the product,
Yes.
the corresponding z's, and then.
And that's the upper bound by delta L minus 1, yeah? Then you have to upper bound the product of the first 2 to the power L minus 1 many z's, that's at most. Well, the z's are in these intervals, basically, minus AA.
So it's a to the power of L minus 1.
A to the power 2 L minus 1. I have 2 L minus 1, 2 with exponent L minus 1 many. So we get this part, and this 4 doesn't hurt us, so I just make it larger by having 2. So that's the point here. And now you have a recursion, and have to solve the recursion, and that's it. Or any questions up to that point? Now we make the same thing, and now we have to see what delta Q is. And you can plug it in here, and recursively plug it in, but you can also imagine to plug it in, and then imagine to make an upper bound, and then write down the upper bound, yeah? That's the way I'm doing it. So you start with delta Q, you get this guy reducing this to delta Q minus 1, and you have this guy fixed once, yeah? Then here you make the same thing with Q minus 1. So again you get this same guy plus this one, this times with Q minus 1 instead of Q. You make the same, and until finally you end up with delta 2, and for delta 1, and then we also have this guy, yeah? So we have each time in the sum, we have this guy, so I can multiply this guy out. And then there's a sum left here. And the sum is what? And that's the ugly part. And I don't need an exact bound. I just need an upper bound which is sufficient. Well, finally I have a 1, 1 here. I have a 1, I have a and then I have all these guys here, yeah? And these guys multiply up, and I have this 2 times going up here. And I forget about all these guys and just use the largest one which is happening of these guys here, and the largest one which is happening of these guys here is, if I end up with something with 4, maybe 1, 2, until 2 to the power q minus 1. The same for A. 1, 2, 2 to the power q minus 1. And then I get one addition from this 2 times here. I get a 1, 2, 2 to the power q minus 1. And what I make as a rough upper bound, when you multiply out, I replaced the guy which was here all the time, this guy, I replaced by the maximum term occurred all the time, which were all the one, or was an upper bound on the largest one. If you don't see it, then just plug it in and divide it, and you will see it's the result. More questions? Please?
What happened to the 4 to the power of minus
What happens to the 4 to the power?
r from the...
Oh, I've forgotten the 4 to the power minus r, which is that, yeah? Very good. We have from this one, we have a 4 to the power minus r. Thank you very much. Because otherwise I would have a problem here. So this was basically the guy which was all the time in. And I multiplied it up here. Then I replaced the product of these guys by a larger one. And we have this 2 basically gives this one. So there's a rough upper bound here, but I think it doesn't hurt me too much. And now the question is, okay, what's that? That's the geometric sum. You know it's 2 to the power q minus 1. You know that q was equal to log 2d ceiling. So it's less equal than log 2d plus 1. So that will be less equal than 2d altogether. So you think these guys are 2d, these guys are 2d, and then I have a 2 here with a 2 there, I make a 4, I add this 4 here, so I think I will end up with, well, we have a 4 with exponent 2d, but I get here something like 2d, and I have an additional 4. I have an a with exponent 2d. I have here an a with exponent 2d gives an a with exponent 4d. And I have this 2d where I use this 2 and this 2 already here, gives you a factor d, and I have the 4 to the power minus r. And that should be my assertion, I think. we are done. Questions? Then I need 5 minutes for cleaning the blackboard. We have 10:46, or I guess 10:47, so I may go on with 10:52. Okay, would like to go on. And now we are ready to prove our main result in this chapter. And then the approximation theory is over, and we will start with generalization theory, which is actually statistics. So if someone is wondering where's the statistics in the statistics lecture, it's coming soon. But as I have told you, if you want to analyze some deep learning procedure in a statistical way, or if you want to analyze the error of the deep learning statistic procedure, there are different sources of error. And one error is the approximation error, one error is the generalization error, which will come next, and one error is the optimization error. And if you want to get a total error bound, you need to control all three of these errors. And if you just have one of them, it doesn't help you. And if you want to make derive a result where you get a good error bound, you have somehow to balance all three of the errors. So usually it will be such that if the approximation is very good, then maybe the generalization is poor. So you have to understand how the approximation is influenced by the topology of the network to choose it such that at the same time the approximation and generalization error is small. That's why we have to study approximation, also if you are doing statistics. Okay, the main upper bound is our main result is a bound on the approximation error of some sets of deep neural networks for PC smooth function. So we let PC greater 0. I bound it in a subnorm, and for the borders of the subnorm, I use now a capital A. I use a K in N, which controls the complexity of my network space. Then I define a function space G, which are just sums of deep neural networks, and I make sum k equals 0 to k plus 1 to x and d. And then, well, this sum comes from because we will approximate the smooth function by a piecewise Taylor polynomial. So I have this j1 to d, element 0 to q, and j1 plus jd is less equal to q, and I have a neural network fk, which depends on all these, or which depends on the k and the g1 to the gd. Where fk g1 to gd is in my space of feed-forward neural networks with L layers and R hidden layers and R small. I have to choose L correspondingly, R correspondingly. I choose L as the, well, you will see in the proof why I choose this in this way. It's a cryptical number, P plus D, and look on K. Then I need a natural number, and the second bound is log with exponent 4 of 2 times with exponent 2p plus 3. Again, another number. And make r equal to 36 times p plus 54 times 3. And I didn't tell you what q is, so basically it should make sense if I replace the q just by the p here. And p doesn't need to be a natural number, so I make a ceiling p. Basically, what I use is a p is equal to q plus s, where s is between 0 and 1, and q is a natural number, but I don't want to introduce this. So, and it doesn't matter if I have a few of these terms in the sum, too many or not. Okay. Then we have for any PT smooth function. G from E to R. If I look how well can I approximate my function G by the best function in my set calligraphy G with respect to the subnorm on the cube minus a subnorm minus a d. Then I get a bound of the form C1 times 1 exponent k is exponent p. That's it. Right? Right. And is this good? Well, if you look about this, the L is basically a log k, the depth, and the width is a constant thing. And then you see you have here, how many weights do you have here? Basically constant times the depth, so basically log k many, and you have basically k with exponent d many of them. So the weights is basically the number of weights is k with exponent d times log k up to some constant. The approximation error is 1 divided by k with exponent p, and up to this that I need log, this additional log factor, many weights, I just have this additional log factor, many weights, it's the same result because of these first components. And I should also tell you what the activation function is. So it's a related terms. And you will see in the baptism course next week, or 1 week after next week, don't remember exactly, you will prove a similar bound for sigmoidal networks. So for networks with a special function, suitable special function for the activation function. Questions? Proof should be clear. What we do, we use our results for piecewise polynomials, which are have a similar sum. and then I approximate the terms, these polynomials occurring here by my neural networks, by just seeing these terms which occur, these piecewise polynomials. There will be a huge product. Each of the function I will be easily able to approximate by my neural networks with one hidden layer, and then I just use my f mal d lemma to multiply them, and that's it. So proof. Yeah, and there's another typing error in my lecture notes here. It should be k equal to 1. Well, it doesn't matter if it's k equals 0, but we don't need k equals 0, because for our piecewise polynomials, we will start, or by our local convex combination of polynomials, we start with k equal 1. So now I introduce the q, that p equal q plus beta, for some q in 0. And beta in 0, 1. I need a formula for the local convex combination of Taylor polynomials of G. That was our P of X. And this formula we had this J1 to J Q, we have some is equal to Q. We have this product of the faculties of the J1 to JD. I use the partial derivative of G with J1 in the first direction, J2 in the second direction, and so on. So we have this partial derivative J1's derivative with respect to x1, and the Jd derivative with respect to xd. And I make this at some clever point, xik. We need the product, the monomial, which is x1 minus k. Well, I have a, I use also I, which is not a perfect thing to do. Here I equal 1 to d. And I need this head function, and the head function is the product. So if we want to d1 minus k minus 28 times x minus x by k again j split y. Which means that our P of x is our local convex combination of Taylor polynomials. Previously introduced convex combination of G. And we also already have seen that this local convex combination of G has a subnorm difference from a G of the order 1 divided by k with exponent p. So it suffices to show that I can find a neural network where the subnorm difference between p and the neural network is less than this order. So it suffices to show this there exists f element G satisfying for all x. And of course, the C1 is now a C2, but doesn't matter. Arbitrary constant. Because we have shown that P is close to G by up to C1 times 1 divided by Kp. So if I show that I can approximate these piecewise polynomials, I'm done. Questions? Do you have any idea how to do this? How can I find the G in this space which approximate this local convex combination to this guy? Okay, do you see any similarities between this local combination of Taylor polynomials and the function in my function space?
Sum over the same things.
I sum over the same things. Do you have any idea why I sum over the same things? I have here a special structure of my, or a special topology of my neural networks. These are basically many neural networks computed in parallel, which have nothing to do, and then I sum up their results, their outputs. That's what I'm doing. Why am I using this kind of structure? Yeah.
So that each summand can locally be the Taylor polynomial?
Each summand will approximate the Taylor polynomial. So the idea is each term here approximates each term here. And then with what kind of error do I need here? Well, 1 divided by k with exponent p is not enough here. Because these errors will sum up here. But if I make an additional factor, which is just the number of terms which I have here, so basically I need an additional, the number of terms is k with exponent d here. So I don't need an error bound between each factor and my neural network of 1 divided by k to the power p, but I need something like 1 to the power k, 1 divided by k with power p plus d. We do this one. A bit larger. That will work. Okay, and how can you approximate such a term by a deep neural network? Any idea? I have to choose a function or find a function in FLR, deep neural network, L hidden layers, real activation functions, neuron layers, such that the difference between these guys is small. Yeah? Well, if you look at these guys here, they are products, yeah? Huge product. It starts with some constant factors. I can forget about constant factors, because in my neural network I can multiply any constant factor in the output, yeah? So I don't have to worry about constant factors, and these factors are somehow bounded, yeah? These factors are all less than 1, and this one is bounded by the so I need a bound on the derivatives of my function, then it doesn't. I don't have any problem. Yeah? This will be just a constant. Yeah, I forget about this one. So basically, you have these guys here. These guys, you see, you have 2D many factors. How to approximate with a neural network product of 2D factors? Any idea?
The start of an idea, so the multiplication, you could use the function that we for the network we constructed previously.
Yes, for the multiplication we just used what we have just shown, yeah? We had the multiplication never, yeah? So, but it's not D, it's 2D factors, but it doesn't matter, yeah? So what you need instead now is you need to look at each factor. And you need to approximate each factor. And then you use your multiplication here. So there are two different kinds of factors. What about this guy here? Oh well, okay. I have to correct myself. I don't want to use 2D factors. I just write this with exponent jk as the product with exponent 1 times the product with exponent 1 times jk times. So we have here altogether q, so I need it with q plus d. And you might see that this q, or this q plus d, or the upper bound p plus d, is occurring here. That was the trick which I used here. So if we look at the factors, we can forget about this exponent jk. We just need an xi minus xik of I. How can you construct such thing with a real neural network? And then you need this guy too. But maybe that's the right thing for you to think about it as a homework, and we will make it quickly. It's a quick proof next time. So, any questions? So I will not need long for this. I have not shown any new Excel questions. Sorry, my iPad is again not working here on the beamer. I don't understand it. I will show them on Wednesday, but I have uploaded them already on Moodle. Okay, good. Then thank you very much, and I see you on Wednesday.